At the beginning of class, before we went over the homework questions, I went over a description of the basic idea behind taking the reciprocal of a function, and it's to take every single point, and the word we use is map. We map it to the same x coordinate, but the reciprocal of the y coordinate. So we say that if we're going from f of x to 1 over f of x, these are both graphs. We go from x comma y to x comma 1 over y. And I said at the beginning, before we went over yesterday's work, this leads to all kinds of conclusions, like if y is 1, it's invariant. If y is 0, it's not defined, which means there's a vertical asymptote. All we're doing today is we're extending those ideas to quadratic functions when we reciprocate them. So for example 1, consider the function y equals f of x and its reciprocal if f of x is x squared minus 5. What this is saying is the original function is f of x equals x squared minus 5. And don't forget f of x is y, right? The second function, the new function, what we would call in Math 30 the transformed function, is y equals, and just look at what I'm about to write, is y equals the reciprocal. But I didn't write y, because this y over here is different than the y in f of x. So what we can write instead, let me rewrite that. What we can write instead is g of x equals 1 over x squared minus 5. And the only reason why I'm using f of x and g of x is because they are different functions, so they have different y values. And I hope that you see that this thing that I've put here is the same as me saying y equals 1 over f of x. Or, better yet, now that I think of it, g of x equals 1 over f of x. So I'm going from a function equals something to a new function equals 1 over that same old function. So we want to graph and label all of the functions and all of their properties. So let's start with x squared minus 5. X squared minus 5 is a cakewalk. It's very simple, but just hold off on drawing anything just for a minute. X squared, we know, has a vertex at the origin, and when we go 1 to the right, we go 1 up, and 1 to the left is 1 up. You're not drawing this because this is not x squared minus 5. It's x squared. If we go 2 to the right, we go 4 up, and 2 to the left is 4 up, because 2 squared is 4, and negative 2 quantity squared is 4. So what does x squared minus 5 look like? Don't think I'm using a table of values. I'm not. I'm saying I've remembered these key points, and x squared minus 5 shifts that down 5 points, 5 units. So we should be able to reason out that x squared minus 5 will have a y-intercept of 5, and from that point, if we go 1 to the left and 1 to the right, we'll go 1 up. 2 to the left from the vertex goes 4 up. And we are going to need to know, I just want to check, is your grid the same dimensions as mine? Okay. We are going to need to know the x-intercepts. This function we're working on right now is f of x equals x squared minus 5. So to find the x-intercepts, we let y equal 0. We can add 5 to both sides. The x-intercepts are plus or minus root 5. What we're doing right now is really a review from unit 3, or 4, or whatever unit it was, I guess 3. Although we don't want to write a decimal value, I think it's useful to know a decimal value of the square root of 5. And I don't know why, but I'm picturing 2.2-ish. And 2.2-ish is about here. I mean, very approximately, maybe closer, I don't know. And then, of course, negative will be on the other side. And here's an interesting thing. I don't particularly care here, everybody, about us drawing this function. I think if you draw this function, unless you're very skilled with a pencil and curves, you're likely to make things cluttered enough that you miss the point of everything. Okay? The point is not what this looks like, it's what the reciprocal looks like. But while we're here, if I were to go to x equals 3, will it fit on this grid? Well, 3 squared is 9, 9 minus 5 is 4. Yes, it does. So we also have a point over here, right at the top. Negative 3 comma 4 and positive 3 comma 4. You understand the challenge in trying to draw a smooth curve through all these points? And why I don't want to do it? Because I'll just embarrass myself, okay? But now let's get to, and we'll get to the features in a second. Let's do the new function. I'm going to use green. If you have a different colored pen, that's fantastic. If you don't, I'll show you what you can do. I'm not even going to write down, well, I guess I will write down the equation. The equation will be g of x, the new function, is 1 over x squared minus 5. But we don't need to look at that equation to plot the points. We need to use the rule that every point on the original function becomes this on the reciprocal function. And I literally in Math 30 this morning was helping some students out in the library, and we're doing the exact same thing, but it's not reciprocals. We're doing something different, okay? Where you look at a value of x, a specific value of x, you read the y-coordinate at that point, you do something to the y-coordinate, and you replot it in that same x position. So, for example, if I were to take this point, it has a y-coordinate of 4. It's about to become 1/4, but let's not draw it just yet. It's about to become 1/4. This point is going to stay in the same position, and so will this one. And do you see that if we were to draw this curve smoothly through all the red points, there would be a point about here on the red function. And there would be a similar point about, well, it depends. I don't know. I'm not very symmetrical here. I'm going to go over a bit. Do you agree there would be 2 points there and there? Those points have y-coordinates of 1. We could figure out where they are. We could figure out where they are by putting 1 in for y and finding the x-coordinates. It would be the square root of 6, which is so close to the square root of, what's the square root of 6? 2.3? 2.4. So it's just a little bit inside the halfway mark. But these would be invariant as well. Why are these, and I want to get rid of this point because it's not invariant, why are those 4 green points that are on top of 4 red points, why will they also be points on the reciprocal function? Because y is 1 or negative 1. They're invariant. What about, and here's where it gets tough, and I'm going to give you guys rulers. It gets tough for me because when I draw a vertical line on here to indicate an asymptote, my vertical line is quite thick. But we are going to have vertical asymptotes on the x-intercept positions of the original function because x-intercepts have a y-coordinate of 0, and you are not allowed to take the reciprocal of 0. There you go, Colin. So I'll show you what I'm going to do and what my issue is here in teaching this. I draw this vertical asymptote here, but right away, a couple of these dots almost look as if they're touching it, right? So I'm going to change the thickness of this so that it's really thin. And then the issue I have is, I don't know, maybe you have difficulty seeing that. But, well, I mean, I think when you see where I'm putting the lines, hopefully it's pretty clear. Like there, you can see it. But that's the asymptote. Now this gets really difficult to draw. Let's plot this point after transforming it by taking the reciprocal of y. That point has a y-coordinate of 4, the reciprocal of which is a quarter. This can be frustrating as a student because what you're doing is you're imagining some points now. If I were to take a look at, say, this point, I hope you would agree that if I did draw the smooth curve, the red graph would pass through about there. Well, that y-coordinate is 2, and the reciprocal of 2 is a half. So that's going to drop from 2 down to a half. And the point is, you're going to get this curve here. We already know, and I can draw this in. I'll not make it as thin as the other ones, that the x-axis will be a horizontal asymptote. So these 3 green points on the left certainly make sense. I'm going to push it here. I'm going to push my luck. Do you agree that if I did draw the completed graph, the smooth curve for the red, there would be a point about here? Can we say that that's a quarter for y? That the y-coordinate of this little blob of a point that I'm pointing at, that the y-coordinate there is a quarter? I mean, I can move it down if you like to match that other quarter. The y-coordinate of that original point is a quarter. What's the reciprocal of a quarter? 4, which means that is going to go up to here. And just look at those green points. The green points are asymptotic against the x-axis, and then they curve upwards and are asymptotic towards the y-axis. If you think you want to graph a curve now that goes all the way up to that point at 4, don't. All you want to do is sketch something like this. This is the issue with reciprocal functions. They get packed so closely against asymptotes that you don't have much room to draw it. Well, you have all the room in the world, but don't draw it in that big space. Just draw it in the tiny space. And I hope you see that over here you're going to get the same thing. And at the risk of making this messy, look up here for a second. I'm going to draw in some of the red graph, and then I'm going to get rid of it. That as I draw this red graph from left to right, the graph is going down. What is the green graph doing from left to right? Going up. That's what we said. We said that if a function goes up, the reciprocal must go down and vice versa. And you can see already I'm way off track with my red curve for hitting these ones down here, right? On the other side, I hope you see that the red graph is going up left to right, that the green graph is going down. So how is that helpful? Well, it's helpful because the red graph goes down and then up here, which means the green graph must go up and then down. How are we going to find, what did I just erase? Okay, that's good. How am I going to find some other points? Well, we could take this point, which has a y coordinate of -4, and I reciprocate it, and I get -1/4. And I know that that's probably bigger than -1/4, but I'm making it bigger than -1/4 intentionally, because I'm going to have to do something else here. And similarly, this point is going to be at -1/4. This point is going to be at -1/5. Now, -1/4 is this number. -1/5 is this number. Pretty darn close, aren't they? But -1/5 is closer to the x-axis than -1/4, which means, and that's kind of why I put these -1/4s where I did, because I know it has to go up even further than those 2 points. Well, this totally makes sense now, that it's going to be, and don't push your luck here, I would just draw it to there, asymptotic to there, and I'll just cheat a little bit, and then in the other direction, asymptotic as well. And that's what it looks like. We don't need to graph y equals x squared minus 5. Let's just graph 1 over, in brackets, x squared minus 5. And I'm going to manually set up my window settings to match what I have here. That it goes from -3 to 3, up by 1, and it goes from -6 to 4, up by 1. Actually, I'm going to go -3 to 4. These green curves are going to be so tight down here against those asymptotes, we wouldn't see it anyway. So I would go from -3 you know what? Let's go -3 to 2 for kind of the same reason. I don't think we're going to see much up here because it's going to be really close to the asymptote. Up by 1. I mean, that's not too shabby. What are we asked to do here? I just gave a blanket statement of domain and range of both functions. Can we dispense with domain and range of x squared minus 5? That's a unit 3 question. It's pretty easy. Range x is greater, y is greater than or equal to -5. Domain, x is any real number. What about the domain range intercepts of the important one? Well, x is not equal to plus or minus root 5. This asymptote is at x equals negative root 5. This asymptote is at x equals positive root 5. There is a y-intercept of -1/4. No x-intercepts, but there's a y-intercept. Now comes the most challenging part. Well, not challenging, thought-provoking. What is the range of this function? Sukman? Yeah. Oh, is it 1/5? Thank you. The y-intercept is negative 1 over 5. And now comes a question that you have to think very carefully about. What is the range of this green function? Nobody wants to stick their neck out on that one? I'll give you a hint. You can't say it in one statement. There's going to be two different statements. One statement for what's going on above, and one statement for what's going on below. So what would you tell me about up top here above the x-axis about y? What must y always be? Greater than 0. And not equal to, because there's an asymptote there. So y must be greater than 0. Or what about down below? Georgia? Can you say that from the top again?
Greater, like less than or equal to 1/5.
And you can't put those two statements together. They're separate things, right? This is a weird topic. It's not important like solving equations is. It's not important like trigonometry is. But all of the little pieces put together are important, particularly for 30-1. Let's take a look at the second example. Let's do this on our graphing calculator. And we'll talk about what we would do on paper. In order for you to sketch this function and the reciprocal of it, you would have to solve this equation to find the x-intercepts. Okay, and we will do this part on paper. Let's find the x-intercepts of the original function. Why do we need to know that? Because that's where vertical asymptotes will be. I can multiply both sides of this equation by 2. I don't have to, but I will certainly make my life easier if I do. Giving me x squared plus x minus 12 equals 0. Which factors into x plus 4x minus 3. The x-intercepts will be at negative 4 and 3. I do want us to do that on paper. What does that mean? It means you're going to have an asymptote here. Was it minus 4 and plus 3? Yep. And you're going to have an asymptote here. Is your grid the same as mine? Okay. It's a little off center. If I had to do this again, I would have changed the scale on this, or oh, it doesn't matter. We will also have an asymptote here. I'm about to sketch something which I will erase almost immediately. Since the leading coefficient of the x squared term in the original function is positive, this will be a parabola. This will be a parabola that opens up. Actually, that's not bad. I'm happy with that. I'm going to leave that. I can't speak to the accuracy of the y coordinates, but we're using our graphing calculator here. I hope you would agree that if this is what it looks like, these are invariant. Which means we should see something like this on our graphing calculator. If this is the lowest, and by the way, there's invariant here and here. If that's the lowest point, and we're going to find out on our graphing calculator how poorly or how good I did this, just by freehanding it without investigating it. If this is accurate, the y-coordinate of the lowest point is about negative 1.5. What is the reciprocal of negative 1.5? It's negative 2/3. It's negative 0.6 repeating. The graph should look like that. Well, let's go to our graphing calculator. Let's find out. By the way, you have to, don't use the x squared, x, and negative 12. You have to go to the original. So y equals 1 over x 0.5 x squared plus 0.5 x minus 6. Let's put the same window settings as we have here. Wow. I got a lot of wasted space down here. I'm gonna cut it off at negative 4 vertically. That's, I did not bad. Not bad. If I find the maximum point of that curve, just like I would with a parabola, the y-coordinate is not negative 2/3, it's about negative 1/6, which means this should have been down here someplace. If I would have drawn it more accurately, it would have gone something like this. Who cares? I really mean that. It's not important. What's important is the process. Right. One last example. This is the kind of problem that you would see on an exam. The graph of a reciprocal of a quadratic function has vertical asymptotes at those points. This is 1 over f of x. All right? This is the function after it's been reciprocated. And we are asked to determine the equation of f of x. Okay, if there's a vertical asymptote at negative 3, then there's an x-intercept at negative 3 on the function. An x-intercept on the function becomes a vertical asymptote on the reciprocal of the function. We also have an x-intercept at 4. How can this be? It can be if we have those factors. I have a question for you, and it's a bit of a vague question. I get that. The question is quite clear, but where I'm going with it is vague. Is that the answer to the question? Is this the equation of the quadratic function? It turns out it is. It is. Can you do me a favor and determine the y-intercept of that function we just created, which means you put 0 in for x. Or expand it out, and remember that when you expand it out, that the constant term is the y-intercept. Because finally we're getting to the point where we have all these pieces coming together from different parts of the course. Do you agree the y-intercept of this function we've created is negative 12? Okay. So why do I know that this is correct? Do you know, Georgia?
Because the reciprocated.
Because if I reciprocate that y value, I get negative 1/12. Right? We're done. But what? What if I said, in an alternate universe, what if I said, that? Then this can't be the function. It can't be. Because the reciprocal of our y-intercept has to give negative 1 over 24. Well, if you work backwards, if negative 1 over 24 is the reciprocal of the original y-intercept, the original y-intercept needs to be negative 24, doesn't it? How on earth do we make that happen without changing these factors? Because you can't change those factors. They're indicative of the x-intercepts. So how do you create a y-intercept of 24? Go ahead. Negative 24. You know how you do it? You just put a 2 in front of the whole thing to double it. Doubling it, and this is an important idea for Math 30, is that what you were maybe thinking? Yeah. Hard to put into words sometimes. We do a lot of this in Math 30, where if you have a function with certain x-intercepts, if you multiply that function by any number, those x-intercepts are the same. You just make things taller or shorter. As it is, that's not the question, right? So that's it. Well, I mean, I'm about to show you here what you do, whether it's quadratic or otherwise. The x-axis is a horizontal asymptote. There are vertical asymptotes where the x-intercepts of the original function are, whether it's quadratic or linear. Whether it's quadratic or linear, if y is 1 or negative 1, invariant. Doesn't matter the type of function. If the function goes up, the reciprocal goes down, and vice versa. So everything we've learned is true regardless of the type of function, linear or quadratic. All I'm saying here is 1 to 10 because you don't have to do them all, but yesterday I assigned a number of them that dealt with linear reciprocals. Now do some with quadratic.